Okay, good morning, everyone. So I think today's class, I would like to continue our topics, and it's still related to the uh, the continuations from the line integral. So I will start with the what we call as a green theorem. Okay. So green theorem, we are going to have a new theorem that will connect the line integral to the area of, or the partial derivative with the coefficient from the line integral. Okay, so suppose that we have this a simple connected closed curve, and let the region D, it will be bounded by the C. Okay. So we assume that all region or all points within D, they are all inside the curve C. And we are going to define what we call as orientations. Okay. So this arrow we call as a positive orientations. So this we call positive orientations. This means the direction of the curve. I will write using this one. So single counterclockwise traversal or movement of the curve C. So then we could have two different orientations, okay, within this region. We can have a positive orientations going to the counterclockwise. So let me write here, counterclockwise. Or going for clockwise. Okay, we call it negative orientations. Okay, so this is just a new terms that we are expecting to have in the future. So the Green theorem stated that if C is positive oriented, a piecewise smooth simple closed curve. Okay, so it's a simple closed curve, it's smooth, and we already defined what is smooth means. And then it's also positively oriented. And then the D is the region that is bounded by that curve. If we have a coefficient P and Q, which we defined P and Q in the vector fields, I think a few weeks ago, then if they are going to be partially derived and they are continuous to be partial, then the line integral P dx plus Q dy, this will equal to the double integral with the region D, okay, for the inside of the curve. And then the inside of the equation will be the partial with respect to x of Q minus the partial with respect to y of P. You could remember this Green theorem, the coefficient or the equations with the previous independence of the path that we check. Okay, so if we check the conservative factors or not, what we check actually, we try to find, so recall in the checking conservative, we are checking whether the the py or p with partially derived y will be equal to q partially derived with x, right? And if you see the what it is going on here, it's actually the same structure, the same structure. And the notations, sometimes the notations can be written as this line integral. Sometimes we can write as with a circle in the middle and this c. So we can write something like this. So this means when you see the circle, this means that it will be a closed curve and positively oriented. So this will be positively oriented and closed curve. Closed curve C. Okay. Another notations that could be written for the green theorem, aside from this line integral, is the integrations, and then this will be having a partial Leibniz notations and D for the region D. We can write also something like this. But the meaning is the same. Okay. But most frequently, we can just write line integral with just simple integration C, or line integral with the circle in the middle signifies that it is a closed curve and positive orientations. And this green theorem is also can be taught as a counterpart of fundamental theorem of calculus in calculus 1. It's very similar in the way it's connecting the line integral with the double integrals. Okay, let's see in more details how we could prove this green theorem, although it's a little bit quite long to prove. Okay, first we can express the region by looking at this picture. So we have a simple type 1 region. If you remember, we are going to have a function of x for y for both endpoints. So this if you remember the double integrals, this is the type 1 region. We call it type 1 region, but I think the most important is to define the D. Basically, we say that the x will be a constant starting from A to B, and then the y will be start from function of x, g1. Okay, so we define the D, and then we need to prove, need to show that the line integral p dx, this will be equal to negative double integral of this, and the line integral of the q dy will be double integral partial x of q dA. So this is what we are going to achieve. Okay, and then because we have the definition of D, we can start directly taking that the double integral of partial y of p. We can set up the double integrals using the a, b, and function g for y. And this will be dy dx. And the inside, if we solve for the partials, we are going to have p, okay, and then this will be, turns out, the only integral with the x. So this will be p, and then we put inside the y and change y with g, and then minus the other g. And then all of this, we still have the integration with respect to x. So if we break the equations, or we break the curve C as C1, C2, and so if we could break the C as C1 plus C2 plus C3 plus C4, as shown in the figure, then we could use each one of this path, or C1, C2, C3, C4. So each one of them, we could set up the parameter. So suppose that for C1, okay, for C1, as we did, I think, in the previous discussion, if we, so let's say on C1, x is our parameter, right? And then y is between, or in terms of the C1, y is g1x, the curve, and then the x is between a and b, okay? So the line integral C1 of p dx, we can equal this to set up the parameter x, a to b, and then input x and g1 of x, and then dx. Okay, this is, I think this is very similar to what we have in the line integral as usual, right? And for the C3, if you see the C3 here, since it goes from right to left, we can make it from left to right by taking the C3 becomes negative, right? So if we imagine that we have another C3, suppose like this, but it is going from left to right, we call this is negative C3, right? Okay, so we can use this negative in our calculations to make it going from left to the right for integrations. Or if you would like to stick from right to left, it's okay, but you need to change the signs when we deal with the, because if you see the whole integration, we need to add all this curve, right? So line integral C1, line integral C2, C3, C4, right? So basically we are adding all this curve. But basically, our integration is from A to B, right? But since there is one that is going from right to left, the integration will be actually from B to A in the integration. So that's why I think it's easier also. You see that if we could change the directions, it will become minus. So all the integration will have the same integration from A to B. Okay? If you get my point. Okay. So let me write here. So the C3. So on C3, we could change to negative C3 so that it is traverse from left to right. So this is taking the x as parameter, and y will be equal to the second curve of g, and the same endpoints for x from A to B. So then the C3 this will be negative, and I will write negative C3 like that. And this will be equal, changing the, should be negative, and then AB, and then we change the x and y, and then the x. Okay. For C2 and C4, we could just make it because they are only a constant, right? So we can say that on C4 or maybe on C2 and C4, x is constant. So the x is 0. So nothing, right? Because in the integration it will be multiplied with 0. This one? Maybe the whole thing better. So then the whole line integral, so we can write here. I think I will make it a little bit smaller and maybe going up a little bit. Okay, so the end, the line integral p dx, it will be, this is C1, let me write completely, plus C2 plus C3 plus C4. So this will be equal a b b x g1 of x minus the C3. So a b b x g2x dx. Sorry, I forgot dx. And then from this expression, we can see that the negative part is coming from the one we have. So this could be equal d and the same way we could get from the q dx by taking the type 2 region. Okay, so we could, for example, we first getting this type 1 region, we could have another for example like this, and maybe this is having h1 of y, h2 of y, and then we can do the same thing. Let's say this is from C to D to make it different from this one, and then all this we can take into like C or C, let's say C1, C2, C3, C4. Okay, and to do the same thing, we could get the same or similar method within this, and that's when we have the same reasons. Okay, when we partially, if we want to partially derive this. And by combining these two, we could get the green theorem. And now let's look on some examples how to use this green theorem in the applications. So basically, green theorem, we can use the line integral and then convert them into double integrations. Okay, so let's start with the first one here. So suppose that we have the line integral x to the power of 4 dx plus xy dy, and then the curve will be based on line equation or line segment from the point 0, 0 to 1, 0, and then another line from 1, 0 to 0, 1, and then the other from 0, 1 to 0, 0. So, so if you want to evaluate the line integral, we can do the first method is the same as we did previously. We can split the curve C1, C2, C3 like usual, or because now we know we can have the green theorem, we can express the line integrations in double integration. But we need to define the endpoints, right? So at least we have the line equations defined by the point, and we get 1 minus x, and this is a constant. So we can, I think let me write the general formulations that you'll see a lot. Okay, that's basically the general formula. So first, we need to notice that this is counterclockwise, the direction. So we say that it's already positive, okay, positive orientations. What will happen if it's negative? Basically, you need to change a little bit the formula, but I think I will get into that later on. So this is positive orientation. So green theorem works as it is directly. So P, from the equation we have x with power of 4 and plus xy dy. So this will be P, this will be Q, right? First, we could state the partial first. So P of with respect to y will be 0, right? So just write 0. And then Q with respect to x will be y. Okay. So basically, we can write this in double integral. The Q is y minus 0. Okay. And then we can state the dA. We can use dy dx or dx dy, depends on the situations. Okay? So now I think I will take constant for x from 0 to 1. So I will take this 0, 1. So I will focus from here to here. Okay? And then the y will be the line, this line, and this line, right? Okay. So the line on y is 1 minus x and 0. And then this will be dy dx. And then we could take the integration as usual. So take the integrations of y. This will be half y squared. And then input 1 minus x and 0. So we are going to have let me just write here how 1 minus x squared is 1 minus 2x plus x squared dx. We can take this out. This will be 0, and this will be 1 over 3. This will be 1 over 6, okay? So we get the result 1 over 6. Another view is we can just use line integral as usual. So we can use the C1, C2, C3, and basically we can write the integrations. We can also separate become these 3 separate line integrals, C1, C2, C3, and then each one of them we can set up which one is the constant, okay? Which one is the one that will be the variable, and we can, I think if you see the structure of the equations, if you want to use this part, I think it's also easy. We can, I think, change the y into x, right? Because we can set the x as our parameter, and the y we can get from that line equations that we can take differential. So dy is minus dx. So this will be minus dx, okay, in the C2. Okay, in the C2. We could use this as the structure also. Okay, you can try the line integrals. Okay, example 2 is another green theorem applications, and you could see when you are going to just using the normal line integrals, split the curve as usual, or when you need to convert into double integral using the green theorem. So taking the example 2, we have the line integral 3y minus e with power sine x dx, and then plus 7x plus square root of y power of 4 plus 1 dy. And as the curve is x squared plus y squared equal 9, a circle. So because we have the circle for the curve, so I think it's best to change into the polar coordinates. So if we write the equation, let me just write the equation first. So line integral is 3y minus e this will be d dx of the 7x plus I think I will make smaller. And this will be minus the partial 3ye, okay, and then the a. Okay. So change the polar. So x is r cosine theta, y is r sine theta. Or perhaps we could solve this first. Okay, solve. So we can write to be qx is 7, py is 3. Okay. I think no need for conversion this one. We can just using directly the double integral for the circle. So circle, remember the outside of the integration for polar will be our angle, and the inside will be so this r will be equal 3. So we can use that from 0 to 3. Nothing in between, it's a full circle. And then this will be 7 minus 3, okay, and then r dr d theta. Okay, this is from calculus 2, double integrations in polar, right? So this will be 4r dr. We could 4 can be take outside, and then we can separate the angle and the r. So this will be d theta, and then this will be 0 r dr. Okay, so this will be 8 pi. This will be half r squared. Oh, why is r? Should be 3. So half multiplied by 9 is 9 over 2. So 8 divided by 2 is 4. 4 multiplied 9 is 36. So 36 pi. But instead of using the method for polar double integrations, I think up until we get the idea that so this could be also written as 4dA, okay, and we know the area is just a circle, right? The area is just a circle, which means the circle has a radius of 3, which means the area of the circle itself is 3 squared will be 9, right? So we could write that the area of circle is pi, 3 squared is 9 pi. So we could get this and just multiply with 9 pi and then 36 pi. So no need for using the double integral in polar. We could go directly to calculate the circle of the area and multiply with the 4, right? Okay. This is just to show you we can apply the green theorem with this, and you will know when you can apply and which one is the best way to solve. This can be solved also. This looking at is a circle, right? So basically the area is, we can get the area is 9 pi. So then this area here is basically 9 pi, and then we just multiply with 4, and that is our double integral. So the green theorem especially works in polar if the curve is having a polar curve that may be not easy to be defined in area. Maybe it has some special curve. Like in your polar curve, we have something called the limmason, right? Or even the cardioid, and so on and so forth. If, for example, if you know the p of x or q of x that's going to be 0, then the whole double integral will be also be 0. This is just a notes here. Then if p is equal q is equal 0, then all this stuff will be 0, okay? No matter the value in the region. Okay, let me move to the next page. So this is just a quick example how we are going to use the green theorem. Another application of the green theorem is to find the area of D. Okay. So the area of D, if you remember the double integrals, let me start with the double integrations. So in calculus 2, we learned that the area of region can be written as the double integral of dA, which means if you remember how it works, the double integral is actually a volume, right? So if you remember, if we have the surface like this, so let's say this is z equal f xy, and then this is basically the projections. This is the dA, right? So the area can be thought as if z is equal to 1. So that's why we could find the area of the region using the double integral, okay? So we in green theorem, we are going to apply that this differences between the q partial x and p partial y will be equal to 1. Okay, because the area of D, since this is equal to 1 dA d, right? Then in green theorem, we would like to write that these two differences with equal to 1. And by doing this, then we can have some possibility for what it will be. So if P, or let me write here, is a possibility. Okay. Let's say if P is 0, then Q, to make it 1, then the Q need to be X. Okay, because when it's partially derived with respect to X, it's become 1, right? So we can have that. Or if we have P is negative Y, because if it will be multiplied with the negative, so it's become 1, and Q will be 0. Or we could have P, so this is 1, 2, 3. P is negative half Y, and another half with the half X. Okay. Oh, Q, sorry. Because they are going to adding it, complete each other and getting 1. So we could have these 3 possibilities inside the equation. So we could have the area. So the area means the area of D. Okay. We could have the line integral x dy. We can have, or we can have the negative line integral of y, the second one, and the third one we could have half and x dy minus y x. And this means that this could be the area B, the area of B. So we can use that to find the area. You can use the green theorem to find the area. So then how we could choose the right line integral? It depends on the equation. It depends on the equation. We could have, for example, uh, some parametric curves. Maybe easier to be fit in with the first one or the second one or the last one. I think the last one, because it works for both sides, it will be generally preferable. Okay. Okay, how to use this? We can get example. Okay, we can get the example from this one. So if we have an ellipse, x squared over a squared plus y squared over b squared equal 1, then if we want to find the area, we can use parametric, or if you remember, to get in the parametric of the ellipse, we can use the let the a, or let x equal a cos sine t, okay, and then y will be b sine t, because it will fit with the equations which cosine squared plus sine squared is equal 1, right? So we can use this, and then taking the ellipse its full angle from 0 to 2 pi, we can imagine that the t will be going from 0 to 2 pi as well. Okay, let's take a break for a while. Okay, let me continue this part. So if we choose the third equation, the half x dy y dx, so we can write here the area of the ellipse is half. Okay, and then because we are going to change the x and y into parameter t, we could use the this xy parameter. So let me write the x part. This will be negative a sine t dt. This will be dy will be b cosine t dt. Okay, so we are going to multiply. So this will be half. And since the t is from 0 to 2 pi, that is our curve. X is a cosine t, and dy is b cosine t, and then dt, minus y will be b sine t, and then dx is negative a sine t, and then dt. So we can solve this, and we get ab cosine squared t, and negative becomes plus ab sine squared t, and this will be dt. So this is the result, and cosine squared and sine squared become 1 if we add. So we can have this is only ab, so this will be and ab is a constant, so ab over 2 of dt, so it's just 2 pi. So the result will be pi ab. Okay. Now, the green theorem, we can transform, basically we can transform line integrals, become double integrals, and we can find the area of the region D by taking this into the these equations here, which we extend these equations from when we have the green theorem, the partial x of q minus partial y of p equal 1. We can have three possibilities, okay? And then we can apply that for finding the area of the region. Okay? And another perspective is we can extend the green theorem and by taking, for example, if we have a curve like this, we can split the region becomes two. Okay, so suppose that the whole region is D. Okay, so the whole region is D, but we can split this. Suppose that we have this splits, and we could say that this will be D1 and D2. And then if you would like, we can also make, for example, if this is the directions, this is C1, okay, for the left part, and we are going to have another one that is direction over there, C3, and this will be C2. But for C2, to make it complete for D2, we need to have another one that is going down, which is negative C3. And this can be worked for our extended version. So let me explain in detail here. Okay. So if we have this, okay, we can make it the region. So suppose that the D is actually a combination between D1 and D2, and we need to also make sure that D1 and D2 are simple region. Okay, both are simple. Okay, the boundary for D1, so D1 will be C1, C3, and boundary for D2 will be C2 with negative C3. So if we apply the green theorem for both these two regions, we can apply them. In the first one is the curve will be 1 and 3, and then apply as usual. So this becomes D1, okay, and then this will be DA. And the second one become D2. Okay. Okay, if we add these two, because of the curve on the C3, because of this, if we add these two, then this C3, they are going to be both get cancelled, right? So basically, we only get, so if we add, let me write here, if we add these two equations, line integrals on C3, okay, use the and negative C3 will be cancelled. Will be cancelled. Okay, so we get line integral C1 and C2 And basically, if we maybe we can split becomes more than two, like for example this one, then this is also applied, that this curve here will be cancelled out, so then you will have only like C2, and perhaps this is the curve here and here and here and here, here and here. Basically that is the green theorem. So we could use this analogy to solve the region which is not simple, but we can make it simple by splitting the regions. Like if we have a hole, for example, if we have a hole, like for example here, we have like a hole, for example here, like that. So this is our D, and suppose that the curve outside is C1, and we have another curve here, which making the hole is C2. So this is, it seems that this could be a problem, right? Because we have a hole. But because we can split, we can maybe split here, or we can make it split here. Okay, so that we can make this into a simple one, or without a hole. Okay. So we can make it maybe here, okay. So then we can introduce this another curve here, which will be cancelled out just like this example. So we can focus on this curve here and the curve here, here, and here. Okay. Okay, I think we can go for example how we could solve some maybe not simple region, but we can make it simple. Okay, so let's see the example here. So suppose that we have a line integral. We have the equations y squared dx plus 3xy dy. So we have our p, we have our q. C is the boundary of the region D, semi-annular region D, upper half plane between the circles, and so that we have two circles. Okay, so if the question didn't give you any visuals, you need to draw the circle. Okay, and then we need only this the half part of it. So based on the picture, we could so if we are uh, not getting the corrections from the green theorem, maybe we are having difficulty to define the circles. Okay, but we can divide the y-axis, becoming this region here. Okay. So we could write in terms of polar. So write d in polar. So d in terms of r theta, which is the radius is from 1 to 2, right? And the angle will be from 0 to pi. So this will be from 1 radius to 2, and then 0 angle theta to pi. So then the line integral we can write, let me write the double integrals, and this will be q of x, which is 3y, and then minus p with partial y, it's 2y, and then the a, this will be y, and this will be y, and then the d will be taking into the double polar integration, so 0 pi from the d, and 1 and 2, and this will be y will be changed into r sine theta, and don't forget to apply r dr d theta in double polar, and this will be solved by we take the r squared with r and the sine theta with the d theta, so we can separate this. Okay, so sine becomes a negative cosine from 0 to pi, and r squared becomes 1/3 r cubed from 1 to 2. This will be 8/3 minus 1/3. It's 7/3. And the cosine theta will be a negative 1, 1 plus 1, 2. So 2 multiplied 7 will be 14/3. Okay, another perspective on using this green theorem, okay, is if we have any positive oriented simple closed path, then all the line integrals of f dot dr, which is related to our previous fundamental line integral and the works, this will be equal to 2 pi. Okay? For every positive simple closed path, okay, that's going to be circle around the origin. Okay, so if we consider C can be any closed path, and we can consider the circle counterclockwise of C, so C prime, okay, inside the region. Okay, and then let's say the circle has a radius a. So assume it has the radius a, which will be small enough that the C prime lies inside the C. And the D, assuming bounded by this 2 curve. So if we make the within the extension of Green theorem that we previously discussed, then the curve or the boundary of the curve will be, so the D is, okay, this is if we thought that this could be split out, becomes this and that. So this is D1, D2, and because, so we could think this is C, and this will be, let's say, C2, and then we have another C prime here, and then C3 or C2, and because this will be cancelled out with the other region here that is having another curve, then we only have this and this, right? At the end of the day, we only have that. So we could write down the general line integral okay, and then this becomes double integral of D okay, we now have the relations for the F. So F xy is negative y over x squared plus y squared plus I. This is x over x squared plus y squared of j. So then we are going to use quotient rule for both of them. So this will be the q, if we give to respect to x, then we have on the bottom side we have the squared, and then we have the x squared plus y squared, and then minus the other part, but I will write the results. Okay, result is this, and then for p we do the same thing. This will be the same. okay? And then we have negative x squared, negative y squared, but we are going to minus 2y and then y squared. So this is another one that is going to be the same. So since we have the same results between these two, this will result in 0. Okay? So what does that mean? That means that the curve for a line integral, both c and c prime, they are going to be the same. So that is the f dot dr for both curves will be the same. Okay. If we use the parametric, if we parameterize that, we have the factor r, that is a cosine t plus b sine t, and stated that it's from 0 to 2 pi. Okay, for the circle, okay, for the circle in the middle. Now, if we take the f dot dr, this will be equal to c prime f dot dr, which we can use the vector r, okay, which we define as a circle in the middle of the whole region. Then this will be equal to, we're using the t, now we change r into t, so this will be 0 to 2 pi, and then f of rt, and then this will be r prime t dt. Okay, so we can input all the r and then take the derivatives of r and then take the dot product. Okay, take the dot product. So we can think r or r prime, we can take derivatives with respect to t. So this will be negative a sine t I plus b cosine t. Okay, that's for r prime. And then rt, we are going to substitute this into this. Okay, so we are going to substitute into the y x squared plus y squared by taking the y is b sine t, and then x squared will be a cosine t, and then multiply both of them with the sign here. Okay. Oh, I think not b. Sorry. Should be same a. The coefficient should be the same. Because the radius is a. I forgot. Okay, radius is a. I forgot to mention. Radius is a, so it should be a. So apply the r of t, substitute, and we get y will be substituted with this. And then plus and we have a squared cosine squared t plus a squared sine squared t dt. So we will get sine squared cosine squared will be 1, so this will be cancel each other, So a squared and a squared also will cancel. So this will be equal to 1. So this will be equal to 2 pi. Or this will be dt, and this will be 2 pi. So from what we have here, we can have some simple connections for just a small notes, which we are going to use this for future references. So if F is P and Q vector fields, okay. So if F is a vector field on open, simple region D, and P and Q partially derivable continuous, and these two are equal through all the points in D, and if C is any simple closed path in D, and R is basically region that the C enclose. Okay, so R is inside the C. Then the Green theorem will give you, I think, make it smaller. So the line integral enclosed positive orientations f dot dr. This is equal line integral p dx plus q dy equal the double integral r and the Green theorem, which resulting, because the partial the same, this will be equal to 0. So we see that the line integral f dot dr will be equal to 0 for any closed curve C. And this is also a confirmation that this is the independence of the path in the region D. Okay. So therefore, I think I can write here to say, resize a little bit, that the f dot dr will be equal to 0 for any closed curve therefore this line integral is independent of the path. So that follows that the f is conservative. Okay, so this could enhance our knowledge from the previous fundamental line integral on the independence of the path. Okay. So that's the green theorem. Okay, so next Monday we will have a quiz up until the fundamental of the line integral and the independence of the path. Okay. So I think looking up on the exercise, I think that will be most of the content for the quiz is basically from that exercise. So Monday, 1 hour class, but since it's only a few contents, so no A4 notes for quiz, but you can use calculators, okay? You can use calculators. But for final exam, you can prepare the A4 notes, okay? Okay, so I think I will end up until here. We are going to see again in the quiz and if the continuity for the chapter will be next Friday. We are going to continue the curl and divergence. So I think our finals, perhaps we could finish the most of the topics in the vector calculus, I think up until the surface integrals, I think. Okay. Surface integral or Stokes theorem, okay, or Stokes theorem. I think I'm quite confident we can have up until that. Okay.